this is your resolution, right? An X-ray complement, typically micrometer. And all these dimensions here, they depend on the material. So if you have gold and carbon, is very different. Carbon will be like this, because it's a light material and the electrons didn't go very far. Gold will look more like this, right? So that's why if you buy an electron microscope, Tescam will give you a gold sample to check the resolution, because they will say you get the best resolution on gold, and that's when you check the resolution. Okay. Well, the electron is a particle, and as you know from physics lecture, it has a wave nature too, right? And it's very simple calculation from school. I just want to focus here on the wavelengths you get at different acceleration voltages, and there are a couple of very important things that come out of this little physics here, right? So if you do the calculation here, so this is a de Broglie relationship, and then you take the moment and do some whatever. But what you do actually, you take the energy of the electrons, and the energy depends on the acceleration voltage. So you know it's different if you're accelerated of 100 volt, 1,000 volt, 10,000 volt, and so on. So this is 1 volt, 10 volts, 100 volts, 10,000 volts, and this is a million. So this would be a high tension transmission electron microscope. This would be typically our scanning electron microscope, and this is maybe low voltage operations, so at a few hundred volts in some microscopes. But you see, if you calculate the wavelengths of the electron, you see that in nanometers, that you see in the scanning electron microscope, we are at 0.01 nanometer, typically. So you know, if you do light microscopy, you do a diffraction limited. That's why you can't go below 1 micrometer, okay? But we are here at 0.1 angstrom, so there is no problem in diffraction limited in the electron microscope, okay? The wavelength of the electrons is 0.1 angstrom. We want to look at 10 angstrom, so we are fine, it's not a problem. But if we run into other problems, there is some other things we have to take into account, right? But for the time being, electron wavelength is not a problem, that's nice. If you think about the energy, though, so if you do later analysis, it means that if we have light elements and we hit them with an electron of this energy of 10 keV, we can take out electrons, so we can kick out electrons from lower shells, from the K shell, you know, you have K, L, M, and so shells on. So you take out an electron here, and then we can actually get an electron down to this level, and the energy difference is very characteristic. Very characteristic. And therefore we can use this for analysis of our sample, for chemical analysis. Another thing is, if we talk later about diffraction, I don't know if you've heard about X-ray diffraction, you know, there is a Bragg equation, 2 times the lattice distance times sinus of the Bragg angle is n times lambda. If you think about this equation, you know, if you have seen X-ray diffractometer, right? So Keith, who just arrived, one of our ESRs, he does a lot of X-ray diffraction, right? So the diffraction angles are 40, 50, 60 degrees, something like that. However, if we have, you know, it's 2 times the lattice distance times the angle equals n times the wavelength. And if you want to study this, the angle has to be very small if the wavelength is very small. And because we are here at very small wavelengths, means also that the diffraction angles in an EBSD pattern that we see is in the order of 1 degree or something like that, right? It's not tenths of a degree like in X-ray diffraction, it's only 1 degree, okay? And it all comes from the wavelengths, right? Not diffraction limited, we can do chemical analysis, and